Hello everyone, welcome back to this online class. Today we are going to look at the Fourier transform, and in particular we are asked to find the Fourier transform of the function defined by f of x is equals to x if the absolute of x is less or equal to a real number L, and it is 0 if the absolute value of x is greater than L. L is a positive real number. When you write L, a member of R plus, it means L is a positive real number. So let me write it here, that L is a positive real number. So then how do we find the transform, the Fourier transform of this function? Solution, we are going to say let me use another color. We say let F capital be the Fourier transform operator. If that is the case, we need to find the Fourier transform of f of x. But then before we find it, we can be able to rewrite this f of x. I want us to take note that absolute value of x less or equal to L. This simply means that the interpretation of this one is that negative L should be less or equal to x less or equal to positive L. That's what it means. So therefore, if I were to represent this in a number line, I will be having something like this. Here we have positive infinity. This side we have negative infinity. Let's say here we have 0 at the center. Here we have negative L, and here we have positive L. So that our function in the interval where absolute of x is less than L, it is this interval from here all the way up to here. Let me use another color. In this interval, our function is x. And by f of x is piecewise, so it is x in the interval negative L to positive L, and it is 0 elsewhere. It is 0 here from negative infinity to negative L. It is also 0 from positive L to positive infinity. So that our function f of s can now be written in terms of those three intervals. Now, it's a piecewise function, yes. Now we break down those intervals into three parts, from negative infinity to negative L. And another one is from negative L to positive L. And another one is from positive L to positive infinity. So therefore, let's rewrite our f of x. So you can say that therefore, that function f of x can now be written as the first interval, that is from negative infinity to L, the result is 0. So it is 0 if negative infinity less than x less than negative L. The other part is x, so it is x in the interval negative L less than x less than positive L. And the last one is 0 in the last interval, that is if L less than x less than positive infinity. So I have just written the given piecewise function in a form that will make our work easy when we are integrating or when finding the Fourier transform. So by definition, take note that Fourier transform of any function f of x is written in this way. The Fourier transform of f of x By definition, it is the integral from negative infinity to positive infinity of exponential negative iota omega x. I there is iota, a complex number. I is the same as the square root of -1. So exponential negative I omega x times f of x dx. That's how we define Fourier transform of any given function f of x. And I told you that the I there is the square root of -1. I is the square root of -1. It is read as iota, a Greek symbol that is read as iota. Now, our f of x is piecewise, so we are going to break down this kind of integral into three parts. You see, we are integrating from negative infinity to positive infinity. So you break it down. The first interval is negative infinity to negative L. Another interval is negative L to positive L. And another one is positive L to positive infinity. So we now say that, therefore, the Fourier transform of this function f of x can now be written as the integral from negative infinity to negative L of exponential negative I omega x times f of x dx. The second interval is from negative L to positive L, exponential negative I omega x f of x dx. And the last one is from L to infinity, and of the same integrand, exponential negative I omega x times f of x dx. So what is the value of our function in the interval negative infinity to negative L? Look at the value, it is 0. So the result here is 0. What about the value of f of x in the other interval from negative L to positive L? The value is x. So here we'll replace that by x. And what about the last interval? What is f of x when we are in the interval positive L to positive infinity? We are told it should be 0. So this is 0. And you see, when you integrate 0, the result is 0. So where we have the integrand as 0, I don't even need to write those zeros. I will only pick the second integral, because the others will be zeros. So this can now be written as, the integral from negative L to positive L of x times exponential negative I omega x dx. Somebody might be wondering, why have I left this one? Is because we are integrating 0. 0 times anything is 0. So when the integrand is 0, the result will be 0. So I don't need this. Neither do I need this, because it is 0 plus that integral plus another 0, which there's no need of writing those zeros. So now how do we integrate this? Look at our integrand. Our integrand is a product of two functions of x. This is algebraic, and this one is exponential. We are going to use integration by parts. If you look at the order of choosing U, LaTeX, you realize that A, it comes before E. So our U will be X, and the remaining will form dV. But look at our U. U is a polynomial. So you write since U, which is X, is a polynomial, comma, use tabular integration. We're going to use tabular integration. It's easier. It's easier than the parts formula. But it's just a special case of the integration by parts. So what I'll do here, I'll have a column for u, another column for dv over dx. So what is our u? Our u is x. What is our dv over dx? Everything that is exponential negative I omega x. So we differentiate u while integrate the other one to get dv, to get v. The first column you differentiate, the second column you integrate. So what is the derivative of x? It is 1. Integrate exponential negative iota omega x, that will give you negative exponential negative iota omega x divided by iota omega. Differentiate 1, you get 0. Integrate this one, we are going to get, of course, it is positive now, so it's exponential negative I omega x over I omega, and this is supposed to be squared. But I told you that I is the same as the square root of negative 1. So what is I squared? From here, when you square it, you are going to get negative 1. So wherever you have I squared, put negative 1. So this is the same as negative 1 over omega squared exponential negative I omega x. That's what we have, because I squared is negative 1. So what we do, we indicate these arrows in this manner. You see, I have not used this, and also this one. I've bypassed those. So once you have those arrows, indicate the signs. Here we have a plus, followed by a minus. They should alternate from plus, minus in that order. So that arrow means multiplication. Let me separate this. The arrow that you see there means multiplication. So this is how we are going to apply this table. Let's go back to our integral. So this means we take x times negative exponential negative iota omega x over iota omega. That will give us negative x times exponential negative I omega x over I omega. That's the first row, the first arrow I mean. The second arrow, I'm going to take 1 times this, because when you simplify, you get this. So 1 times this, then it is, the sign is there is negative. So this negative will cancel with this other negative so that we get positive. Positive 1 times that, we simply get 1 over omega squared times exponential negative I omega x. And remember, we have the limits of integration. We are integrating from x is equals to negative L to positive L. So when we substitute the upper limit, what are we going to get? I'm going to get negative L over I omega exponential negative I omega L plus 1 over omega squared exponential negative I omega L. That's when you use the upper limit. Minus, let's use the lower limit. Now x is negative L, so that will give us L over I omega exponential I omega L, because x is negative, so it will cancel with the other negative, then plus 1 over omega squared exponential I omega L. So how else can we write this? This can be written as, I want to open the bracket, negative L over I omega exponential negative I omega L plus 1 over omega squared exponential negative I omega L minus L over I omega exponential I omega L minus 1 over omega squared exponential I omega L. So I want to combine the like terms. Look at this one. Let me start with this and this. I can see L over I omega is common, so I can factor out that. This can as well be written as negative L over I omega, which is common, so that inside we have exponential I omega L plus exponential negative I omega L. Another like term is 1 over omega squared. We also have it here. Let me factor out negative 1 over omega squared. So minus 1 over omega squared, so that inside we have exponential I omega L minus exponential negative I omega L. Now, how else can you write this? This can as well be written as, I want to multiply both numerator and denominator by 2. So I'll have divide this by 2, and also here I introduce 2. The same here, I divide by 2. This one I'll divide by I2. And here I have to multiply this by I2. So let me just rub the one here. I'm multiplying this by I2. So I'm going to write I2. You see what we have there? So now, what is this that we have in the brackets? And what is this again? I want us to take note that cosine of theta is the same as exponential I theta plus exponential negative I theta divided by 2. Also, sine theta is the same as exponential I theta minus exponential negative I theta, everything divided by I2. So that's what we have. And so we can now write our answer as, remember on the left-hand side was the Fourier transform. So therefore we can now talk of the Fourier transform of f of x to be equal to negative 2L over I omega. This is cos, in this case our theta is omega L, so omega L, that's our theta. Then minus, the other one is I2 or 2I, whichever, I2 over omega squared times, this other one is now sine omega L. And so this is our Fourier transform of that function. You see, I can take this I up so that what should we get? This can be, remember, 1 over I is the same as I over I squared, which is negative I. So this thing you can write as negative 2L over omega times negative I. That is simply I2 times L over omega. See, 1 over I is negative I. So then this one is cos omega L minus I2 over omega squared sine omega L. And so I2 is common, so this is the same as I2. Then this is L over omega cosine of omega L minus 1 over omega squared sine omega L. So our result is a complex number. This thing here is usually called complex Fourier transform. Look at our definition of the Fourier transform where we started. It is the Fourier transform. Usually we call it the complex form of the Fourier transform of a function f of x. So our answer is a complex number, which is a function of omega. Remember, L is a constant, is any real number. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When you meet next time, we look at other problems in Fourier transform. Bye-bye.